Okay, welcome to the Theoretical Computer Science Seminar at Jagiellonian. Today we have Bartłomiej Kielak, who is a PhD student at our university. He works mostly in extremal graph theory under supervision of Andrzej Grzesik, and today he will tell us about inducibility of small-oriented graphs.
Thank you for the introduction. So I'd like to continue on the topic of Turan type problems, which were mentioned a week ago, but with two small distinctions. One of them will be that we'll be discussing not hypergraphs, but oriented graphs ultimately. And the second distinction would be that we will consider kind of different notions, which I will introduce in a minute. But first, I think I should start with introducing my co-authors. So one of them is Andrzej Grzesik, who is present in the room, but you probably cannot see him. And the second one is Łukasz Bożyk from University of Warsaw. Unfortunately, he also couldn't join us today, but maybe you'll have opportunity to see him on some different occasion. So let me proceed to the main notion of today's talk. It is called inducibility. And to define it, we start with some fixed graph on k vertices. We'll call it graph H. And we want to ask what is the probability that if we sample at random k vertices from some large graph G, then those k vertices would induce a subgraph isomorphic to graph H. And this probability we denote by small I of H and G. Of course, as in Turan type problems, we are interested in the maximum of this value over all graphs of fixed size. So we take just the maximum over all graphs on n vertices. And finally, we would like to go to the limit. And this limit always exists, as it was proved by Pippenger and Golumpitz. And we call it the inducibility of a graph H. So that's about the definition. And what about the properties? So one of the most basic one is that the inducibility of any graph H is at least this fraction, which you can see, like k factorial divided by k to the power of k minus k. And it is true for any H. And it would follow from some iterated construction, which I will describe later. And also, they were able to determine the inducibility of a complete balanced bipartite graph in their work. So they obtained some expression, and this expression is just like pick a complete balanced bipartite graph on n vertices and just compute the inducibility. I mean, the probability that we will see our smaller bipartite graph. So that's just the value. So the external construction is kind of boring. So we also had some following results, and it is due to Brown and Sidorenko from 1994. So they were able to determine the inducibility of a complete bipartite graph, but not necessarily balanced. So we have just any possible values of S and T. I mean the sizes of parts in the partition. And I got some hello. And here we have just the answer given as the maximum of some value of some polynomial. So if we fix some S and T, then we can find what is the proportion of parts in the external construction, because here the external construction is again a bipartite graph, complete bipartite graph. But the question is, what should be the ratio between the parts? So they didn't give the explicit answer. Instead, they just said, just do it yourself. And also, they gave a similar description for the more general problem of R-partite graphs, complete R-partite graphs. And again, this long expression is just saying that we should look at some large k-partite graphs. So here we have some k, which is at least R, but possibly larger. And the optimal, extremal construction would be some k-partite complete graph. So 1 year later, we got another result by Bolobash, Egava, Harris, and Jean. So they did. So they were working on the same topic, but independently, and they also said something about the extremal graphs for our problem. So, for instance, in case of three-partite balanced graph with each part of size t, they concluded that indeed the only extremal construction would be to take the two-rank graph, so complete three-partite graph on with n vertices on n vertices just. But this is if we consider three-partite graphs, and if we consider r-partite graphs, and we still ask about the extremal construction for r-partite balanced graph with t vertices in each part, then if t is large enough, so if we have many vertices in each part, then actually the two-rank construction with r parts is okay. But otherwise it is not. And their arguments to say that it doesn't work anymore is just to say that actually the two-rank graph with r+1 parts is strictly better. So indeed, as we have in the previous result with Brown and Sidorenko, we need to look at all k-partite graphs with unknown k. So k may be strictly larger than r. So what is remarkable about all those results? So the remarkable thing is that we have a lot of blowups as the extremal constructions. So maybe let me introduce it more formally. So we have a definition of a lexicographic product, which is also known as a composition of graphs, G and H. So roughly speaking, we just replace each vertex from G by a copy of a graph H and introduce all edges like it was in the original. And in particular, we can apply this operation to a graph H itself. So like to compose graph H with itself. And if we repeat it like k times, then we obtain something which is called an iterated blowup of H. So the thing that observed Pippenger with Golumbich was that if we consider the iterated blowup of H and we count how many copies of H we can find inside its iterated blowup, then we obtain at least in the limit the k factorial divided by k to the k minus k. So, but that's not all about the blowups, because if we take any graph H and we consider large enough iterated blowup of this graph H, then actually the extremal construction would be just to take the iterated blowup of H, just on a larger number of vertices. And it is a result of Hatami, Hirst, and Norin. And a few years later, Juster actually determined that again for almost every graph H, the inducibility of H is almost as in its iterated blowup. So there is some factor, it is not exactly 1 as you would like it to be. There is some slight difference. But there is maybe a question, what does it mean almost every graph H? Because here it should be, understood in a way that if we consider the Erdős-Renyi random model on n vertices, so we just take a bunch of n vertices and we say that there is an edge between two vertices with the same probability 1/2 in this case. So if you consider just a random graph from this Erdős-Renyi model, then actually with very high probability, it would have inducibility of this value. And there is yet another result in this fashion, that actually from almost every graph H, so almost every as before, indeed, the inducibility of H is exactly as in its iterated blowup. But unfortunately, so far, this result was not yet published. Okay,